Firstly, firstly we define a probability space. So notice that suppose that you have an experiment E, and now this experiment will not have a predetermined outcome. So we will construct a set capital Omega of all possible outcomes of this experiment, and we will call this set our sample space. Now in this experiment, uh, we can be interested in some events. For example, we want to know that omega corresponds to something or not, and we want to consider the set of all such omega, small omega, which correspond to that thing. So, like, firstly, define a sample space capital omega of an experiment E to be the set of all possible outcomes, and we denote an outcome by small omega. And we say that an event A is a subset of capital Omega, and that the event A occurs if and only if our small omega, which is the outcome, belongs to that subset. So, is this definition clear? Like, mm, it should be intuitive. Okay. So, let's go on to define the event space. So, an event space F is like the set of all events which we want to consider. So, for example, it could be like, suppose our experiment is a coin toss, then the events would be if the outcome is a head or a tail, or like head or tail, and like phi, which is the empty outcome, empty event. And also notice that if we have events A and B, then we want that we can also consider events like A complement, B complement, and A intersection B, and A union B, and so on. So, with these, we have that uh, if A and B belong to F, then we want to have that A complement also belongs to F, and like A intersection B and A union B and so on also belong to F. And now we assign a likelihood of these events, which is our probability measure P. So, now we formalize all of these. So, a probability space is defined as a triple capital omega F and a probability measure such that capital omega is a non-empty set and F is a collection of subsets of omega, so that the whole set omega belongs to F. That means that we can consider the whole set omega, that it is in consideration. And if a set A belongs to F, then A complement also belongs to F, as we saw. And we also need that if AIs are countable set of events which belong to F, then their union also belongs to F. So this thing. Now, these three would actually imply that the intersections and like the other things also belong to F. Now we define the probabilities of such events. So the to define that, we have a probability measure P, which is a function from the set of all events to R, which satisfies that the probability of each event we want it to be positive, like greater equals 0, and that the probability of the omega is 1. And if we have disjoint events ai, where I is again countable, then the probability of their union is just the sum of the individual probabilities. So when we say a set is countable, we mean that it is at most, like, it is finite or countable in.
You're not visible. You're not audible, Tejas.
Wait, like, I wasn't audible till now.
Oh no, only for the last 20 seconds or so.
Oh, okay. So like, did you get the definition of a probability space? Like, did you get the definition of a probability space?
Yeah, that was audible.
Okay. So now we consider an example. So suppose we have a coin toss and we only care about the
I
outcome of
think
the
your
first
screen
coin.
is not being shared.
Okay. So now is it all right?
Yeah,
Okay. So suppose that we toss a coin twice and both the coins tosses are independent, and that we only care about the outcome of the first coin toss. So let's just construct our probability space for this experiment. Now, so uh, what do you think is our set sample space? It will be like the set of all outcomes. So what are the outcomes?
head, 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 tail, tail.
Yes, exactly. So our outcomes would be head tail head, and tail tail. This will be our sample space. Now, what is the set of events which are in our consideration? And yes, so because we only care about heads. So notice that this will be, we want to have to f to at least have the set h, which actually means that because f has to be a subset of the power set, which is the set ht and hh. We also want it to have the set tt and th. So this is because the outcome that the first coin is head actually corresponds to this subset, and the outcome that the first coin is tail corresponds to this subset. But now we also want to consider mm, events like the outcome is tail or head. So we will get that this is our f, because phi will have to belong to f, because that we will see that intersections belong, and this is the whole set omega, which has to belong to f. Now the probability, we define the probability measure as the probability of heads, single heads, to be half, and the probability of single tails to be half. So, and the probability of whole set omega to be 1, and the probability of phi to be 0. So this is an example of, like, how we can formalize a coin toss where we only care about the first coin. So now we will prove some of the properties of a probability space. So, like, uh, I will prove the first property among these four, and then like move on to the next exercises. So, so can anybody tell how we will prove that just from the axioms that we can take countable unions and complements, that countable intersections are also allowed? That if AI are countable sets, uh, are a set of countable sets, then we can take the intersection of AI, which also belongs to our event space. Yes, so try that. It's just like it will be a manipulation of our axioms.
What do you mean by at most countable?
So we say that a set S is at most countable is just to make it clear. It just means that S is countable. So we say that S is countable means that S is finite, or that S is countably infinite, which means that it is in bijection within the natural numbers. So is this clear?
Yeah.
Okay. So firstly, try proving that A intersection B belongs to F, and the similar proof will generalize. So
Since A union B belongs to F and A intersection B is a subset of A union B, so A intersection B also belongs to F.
no. So notice that F is an event space, and we have axioms which say that if A belongs to F, then A complement belongs to F. And we have that if AI belong to F, then we can take unions of AI. So you cannot say intersection that A intersection B belongs to F just because the union of A and B belong to F, because like it is not an axiom that if a set S belongs to F, then its subset also belong. So do you get my point?
Yeah.
So so the idea is that if A union B does belong to F, then its complement also belongs to F. Right. So now if A belongs to F and B belongs to F, then A complement belongs to F and B complement belongs to F, which means that A complement union B complement belongs to F, which then means that this the complement of this whole set belongs to F. But this is just A intersection B, and this belongs to F. So this can be seen as, suppose A is this and B is this, then we know that A belongs to F and B belongs to F. So we will get that the complements belong, and then so because we can change unions to intersections by taking complements. So do you get this proof?
Yeah.
Uh,
Yes.
can you take again the definition of F?
Yes, sure. So we have a sample space, capital omega, and then events are defined as the subsets of the capital omega, and F is the collection of subsets of omega, so that the whole set omega belongs to F. So this is the first thing. And the second thing is that if a set subset A belongs to F, then a complement belongs to F. And the third thing is that if we have finite or countable sets AI belonging to F, then their union also belongs to F. So you can see this as like F being the collection of all subsets which we are interested in, and we make these three axioms. So because to define these F. So is this clear?
Okay.
Now, uh, in a similar way, you can also now notice that the fact that we can take intersections is really powerful because and because like if we have any countable sets A, B, C, and so on, then we can just consider arbitrary intersections to get smaller regions. So, for example, these are the four sets, and then we can take intersections to get all of these small regions to belong to F. So, is this idea intuitively clear?
Yes.
Now, because we can also take unions, so the union of any of like any subset of these small uh, sets like regions will also belong to F. So uh, with this, like we can prove that a lot of things actually do belong to F. So for example, if we have A and B, then because A intersection B belongs to F and A belongs to F, so we have that A complement, which is this region, intersection B will be this region. So we have this region also belongs to F, but this is just like A.
B minus A.
Yes, B slash A. Uh, and like we have in a similar way, we can prove that uh, A slash B belongs to F. So like you get that idea that now because we can take intersections, countable intersections, and countable unions. So if we are given some collection of sets, so we can like almost prove any reasonable thing to belong to F, like which is representable as a set function. And now like you can the 3 and 4 are exercises. So now we prove a very uh, like important result. So the idea is that if our sample space omega is countable, then we can classify all possible event spaces and all possible probability measures like without much difficulty. So this is what you do for finite things. You like almost do for finite things in exercises 2 and 3. So so the general result is that if if our sample space is countable, then like our event space will have to be the power set of some set X, where this set X uh, will correspond to a partition of omega. So like we will prove this for finite things, for like capital omega being finite, and then like uh, so this is in exercise 3, and then in exercise 2 you will classify all the probability measures which can be defined on such a set. So like the countable case is uh, quite similar, but also like a bit difficult. So like let's try exercise 2 first. That so if we have omega being countable, and you are given that f is the power set of omega, then we want to find all possible probability measures p on f. So like keep in mind this definition, like these three, and like try this for a bit. So like uh, the key thing will be this third property, that if we define probability measures on like you can say like basic sets, or like then like by taking countable unions we can define the probability of a countable union of those basic sets is already predefined by our probabilities. So the idea here is that since f is the power set of omega, so we know that each subset of omega already belongs in f, and so we can assign probabilities to like all the subsets of f. And so consider a subset omega, which is just the set containing an single outcome omega, and let the probability of this be pi. So since omega, the a capital omega is countable, so there are so we can index it by I. So like let capital omega be the set of small omega I, such that I belongs to I, capital I, and this is countable. So is this thing clear? Like so this is basically like just the definition of countable. So you can take it to be for now like omega I, such that I is a natural number.
So basically we can label the set with natural numbers.
Yes, like that is almost true, unless the set is finite, which is also like, which is why I have put this I, which can be a natural number or like 1 to m. So but like this is not important, but so the main thing is that suppose you have defined all the probabilities pi on little omegas, then for any subset a
It is
of
just
f,
summation pi of the elements of A.
exactly, so the probability of that subset a is the summation over pi where omega I belongs to a. So that means with these the probabilities of each subset is determined, and moreover, as long as the summation of pi where I belongs to our n say is 1, this has to be true because probability of omega is 1. This is an axiom. So is this clear why this has to be true?
Yes.
Yes.
Yes. So as long as this is true, any such pi actually works. So, any such uh, set of p1, p2, p3, and so on, such that each of them is positive and sum of pi is 1, actually defines a probability measure on F. And moreover, this is by this we have classified all the probability measures on F as where omega is countable. Notice that we needed omega to be countable because when we are defining the probability of A to be sum of pi's, then we need A to be countable because the third axiom only says it for I is countable. So, so is this clear that why this sort of arrangement works?
Yes.
Yes. So also that this sort of arrangement is will be necessary because we can define probabilities on single events, like single events omega, and the probabilities will clearly satisfy that they will be positive and that they will sum to 1 because omega is countable and from these three axioms. So so is that clear?
Yes.
Okay. So this basically completes exercise 2, and the answer is that the classification is that we define the probability measure of omega I to be pi, where the probability of pi is greater than 0 for all I, and the sum of probabilities, the probability of that pi is greater or equal 0 for all I, and the sum of pi is 1. So now we will want to prove that, so if we prove that omega, for if omega is finite, then f will be the power set of some set x, like then by a very similar argument, we can also define the probabilities on that set x. So so now we will try exercise 3, which says that, so the statement is that the cardinality of f has to be a power of 2, but we will prove something stronger. So we will
That
prove
it
that,
is some power set of subset.
yes, we will prove something even stronger than that. We will prove that f is a power set of a set x, where the set x is a set of subsets, is a subset of capital F, such that x partitions omega. So I will define this now. So suppose omega is a set x1 disjoint union a set x2 and so on. Then we say that the sets xi partition omega. Is this definition clear? Just so you can think of it as this. So if this is our omega, then we will prove that f is basically the power set of some of these sets. So for example, if omega is 1, 2, 3, 4, 5, suppose, then we will prove that we can divide omega into some sets such that f is f corresponds to, like, f is 1, 2 comma 3, 4 comma 5, and 5, and 1 and 2 comma 3 taken together, and 1 and 4 comma 5 taken together, and so on. So then f will naturally be in bijection with the power set of, say, call this thing a, call this thing b, and call this thing c, the power set of the set a, b, c. because each each element belonging to the power set of ABC corresponds to the union of A, B, and C. A union of the elements belonging to that power set. And so, is this like intuitively clear?
Yes, it is.
Okay. So now, I won't like completely prove this, but I will give you an idea. So you know that you can take arbitrary intersections and unions. So can you construct the such base sets which actually like work? So can you construct such sets which form a partition and also belong to F?
So the base sets would be a collection of sets that do not have any subset of them in F.
Um, no, like the base sets would be a collection of sets xi, so that yes, uh, yes, that's true. What you said is true. So the base sets would be a collection of sets xi, such that one thing is that they wouldn't have any subset in F. The other thing is that they would have to partition our like omega. So the idea is exactly what you just said, that if we take if we have that the base sets do not have any subset in them, then suppose xi and xj are base sets, then their intersection will also be phi empty, because if they have some intersection, then like we will have we will just have that the intersection is a proper subset of xi, unless like one of them is contained in the other. So like now the question is, how do we construct such sets, and then we will prove properties about these later. So note that F is a collection of subsets which satisfies arbitrary intersections and unions. We will just use these. So now, what if you consider something like this? Take an omega and take the intersection of all the sets such that omega is an element of that set A. So take the intersection of sets A such that omega is an element in A, and and A belongs to F. So this is this the set this which we have constructed will belong to F by the countable intersection thing. Is that clear?
Yeah.
Yes. Now now notice that because of the countable intersections, this belongs to F, and also that if we have any other set T, suppose, which belongs to F, and T intersection A, and suppose that omega belongs to T, then T intersection A will have to be A.
Yes,
Why is this true? So this is
because
true. Yes.
uh, because A is the intersection of all those sets that contain W, right? So if T contains W, then T intersection A has to be A.
Yes, exactly. So this is the idea. So now we have, so basically such sets A which we have constructed will actually be our base sets. So now no, so now I'll just give you the idea. So now we have constructed A1, which is a base set corresponding to some omega. Now we will delete all the omegas which is in the base set, and like construct another base set A2 which corresponds to our omega 2, which is another omega, and so on. And then we will get that the intersections of a1 and a2, ai and aj, would be phi, because simply because like we deleted the elements, and also that their union will be uh, our omega, because this process ends somewhere, and also that these will belong to f, simply because of our like that we have proved, we have like constructed them as intersections of some sets we all which already belong to f. And after this, we have proved that f will be a power set of some the set which correspond to the power, so f will correspond to a power set of say 1 2 till m, where this is am, and this is because of the disjoint union axiom. So a1 a2 till am are disjoint, and like their unions belongs to f, and only those elements belong to f. So like this is just an idea, so you can try to formalize and complete this later. So now, like, we have seen some basic properties of like a probability space. Now now our suppose our outcome is omega, and like we want to know some property about omega. So say that like we want to measure the temperature of some place, and we want to measure the pressure of some place. So one thing we can do is that we can model temperature itself, and by this we mean that our sample space would look something like 1 degrees 2 degrees and so on. Then we will define the probability that temperature is this. And but if we do that, we will need to specify our omega f and the probability measure each time, if we do it for temperature and pressure and so on. But there is a nice substitute which we can do, is that we take the sample space to be, suppose, the set of all uh, say weather states. So our sample space is a set of all weather states. Now we know that temperature, pressure, and so on, these are functions which only depend on the weather state. So temperature is a function of omega, and our outcome is the weather state. So like with this intuition, we will define what a discrete random variable is. So a discrete random variable on a probability space omega fp is just a function x from omega to the reals, so that we have two conditions. So we'll see why these are important. So the first thing is that we wanted to like measure temperature, say. So we will want that at least the event that the temperature is some say 1 degrees is in f. So which is where the second condition comes in. So the event, so in the general random variable case, so the event that our random variable x takes the value small x belongs to f. So this is one of the conditions. And the second condition is that image of x is countable. So so this condition is there because like we are only allowed countable intersections and unions, and so in order to ensure that we have something like the temperature, or say like the random variable x belongs to some set a subset of reals, to be a subset we will have to take unions, and we can only take countably many unions. So this is a very good condition which we need, that image x is countable. So so is the definition clear?
Yes.
Yes. Now the function, since these are already events, So we know that they will have probabilities. So we can define the probability mass function of a random variable to be simply be the probability of the event that our random variable x takes the value small x. So the probability mass function is a function from the reals to 0 1 such that the probability mass function evaluated at x, where x small x is a real number, is just the probability that the random variable x takes the value small x. And by the way, like by this we mean that it is the event which is the set of omega, our outcomes, such that x of omega is small x. Since x is a function, capital X is a random variable which is a function of omega. So now just the elementary properties of a probability mass function is that if x is not in the image of the random variable capital X, then the probability mass function of x is clearly zero, because I mean the event is empty. The event that the random variable takes the value x is empty, and also the sum of the probability mass functions is 1. So uh, are these two clear?
Yes.
Okay. Now just to give an example, suppose that we have two three-sided dice, and like we have taken it to be three-sided just for simplicity. So our sample space omega is uh, pairs I comma j, where 1 is less equal, I is less equal 3, and 1 is less equal, j is less equal 3. So this just shows our outcome of the two dice. Now we take f to be the power set of omega, and then the probability of an event a uh, will be the cardinality of the subset a divided by 9. So this is true because, so can anybody tell me why this is true?
Because
Like we are,
cardinality of A is 9.
what?
Wait.
So a is any subset of omega, not omega itself.
Yeah, because it has mod A elements and each element has probability 1 by 9.
Yes, exactly. So our omega in like as a set is this. And now what if we take the random variable x, which is a function of notice that it is a function of omega, such that x is the outcome of the first die, right? So do you get why x is 1 is the event which corresponds to these three elements here? Because x is 1 is the outcome of the first die, and similarly x is 2 is the outcome of the second die, and x is 2 is the outcome of the first die only. And like if the first die is 2, and x is 3 also represents this set. So is this clear? Like, so our random variable x is just the outcome of the first die. So we get that x is from capital omega to r, such that x of I comma j is I. Yes. So now, because x and y are functions, so and they are random variables, so we can also consider random variables z, which are a function of x and y. So we can also consider random variables which are, say, x plus y and say ax. So this makes sense because we can just define x plus y to be the function which is the which is calculated by evaluating at x plus evaluating at y. So now we give an important example of a random variable. So this is widely used because like it measures whether the outcome belongs to A, where A is a subset, or it does not belong to A. So here is the definition. So the indicator function of an event A, it is denoted like this, and this is a function from omega to the reals, satisfying that the indicator function of omega is 1 if omega belongs to A and 0 if omega does not belong to A. So is this clear? Like,
Yeah.
okay. So just to give an example, so suppose we have a coin toss, a single coin toss, and like we define A to be the event that head appears, then 1A is the indicator function is 1 if our outcome is heads and 0 if our outcome is tails. Yes. So like now we are ready to define the expectation of a random variable. So firstly I will define this informally. So like informally expectation is just the average of the values taken by the random variable. So suppose that our random variable takes values x1, x2, x3 and so on with probabilities p1, p2, p3 and so on. And then since our random variable is discrete, so we can do this in this way. So our expectation of x is defined to be just the summation of xi pi. And more formally, it is this. So the expectation of x is the sum over x times the probability mass function of x evaluated at small x, where this sum is over all x belonging to image of the random variable x. So do you see why these two definitions are like the same? So this is because when we say x, small x, then small x will be the capital X of some omega, and we are summing over small x belongs to image of omega, image of x, capital X. So suppose that capital X takes the value x1 with probability p1, then this sum just counts where x1 belongs to image, so x1 times the probability that x is x1, which is precisely p1, and so on. So like these two definitions are like the same. So so one thing to note here is that here the sum over, because image x is countable, over countable is defined as the limit of the finite partial sums. So for example, summation 1 to infinity of some ai is defined as the limit as n tends to infinity of sum over ai 1 to n, and we can define finite sums like, which is just the obvious definition. And also that, so an infinite sum does not always behave nicely, in the sense that if we change the order of the elements, then the value of the sum can actually change. So to stop that from happening, we will need an absolute convergence of this series, and like, so just take that on faith for now. So now So now I want you to try exercise 4, that prove that the our random variable which we had defined as the indicator function, then the expected value of the indicator function of an event A is simply the probability of the event A.
Can I tell?
Yes, sure.
So indicator function, or what it was, variable or function?
It was function, right?
Yeah. So indicator function is one when the element belongs to A, and zero when it doesn't. So the
Yes.
expected value will be one into probability of that event. So it's the sum of all the probabilities of all elements belonging to A, which is just the probability of event A by that axiom.
Yes, exactly. So, like, to just restate what Pranav said, that the expected value of the random variable 1A is, by the definition of expected value and by the definition of the random variable 1A, is like 0 times the probability of A complement plus 1 times the probability of A, which is simply the probability of A. So here note that, like, our indicator random variable, which is the indicator function, is 1 if omega belongs to A and 0 if omega does not belong to A. So probability that uh, our omega belongs to A will be just like the probability of A. So that's correct. And so now, because we don't have too much time, so I will leave exercise 5 like as an exercise. So it is, it just gives you an intuitive feel why the expected value of a finite random variable which is uniform will be just our arithmetic mean of the image. So now we come to the part where we have a function of a random variable. Yes. So before that, notice this, that if our sample space omega is countable, suppose that our sample space omega is countable, then omega is, suppose, small omega 1, small omega 2, small omega 3. So I claim this. My lemma is that the expected value of any random variable x defined on the probability space corresponding to omega will be sum of the probability of omega I times the random variable which takes its the x of omega I. So can anybody prove this? So first of all, notice that this summation is well defined because we are taking f to be the power set of omega, and also that, so these probabilities are defined, and also this is a countable sum which we can make sense of. So, like, try proving this. So notice that this is also like an alternative definition. This can also be an alternative definition of expectation, where the our sample space is countable, and this is true because our expectation of a random variable x is defined as the sum over the value that x takes times the probability that x takes that value. And when, so if we consider this sum, and uh, first we add only those elements, only add this sum only for those outcomes such that x of that outcome is fixed. So sum of probability omega I, x of omega I, will be equal to the sum of, so if we add this over omega I such that x of omega I is small x, and then we sum these over all x belonging to the image. So, can you see why this is true?
Yes.
Yes. Now, now this is equal to the summation over x belong to image of capital X of the sum of that x small x, because it is given here that the x of omega is x times the probability of omega I. Now this will be equal to the sum over x belongs to the image of x times the sum of the probabilities of omega I. But notice that this is just the probability that x is equal to x, because the event x is equal to x is precisely the disjoint union of our, so the pro wait yes, so it's just the disjoint union of the events omega is omega I. So this is because we defined omega I in this way, like omega is such that x of omega is x. So is this clear?
Yes.
Yes. So like now we have proved that this will be equal to this, which is equal to the sum of x times the probability that x is x. Correct. So we have proved this lemma, and like this is good for intuition that, so if you want to prove results about expectation, so you can just sum over, so if you want to prove expectation value of some general random variable, you can just sum over like uh, the values that x takes to omega times the probability of the event omega, as long as we can reasonably define this sum and these probabilities can make sense. So like now we give some theorems. So so the first theorem is that the expected value of a function of a random variable h of x is the sum of h of x times the probability that x takes the value x. So before that, also notice that suppose intuitively this is our sample space and these are our omegas. So expected, so at each of these points we define the random variable to be a value belonging to the real. That is like the definition. So we want to sum all these values multiplied the probabilities of each value. But this sum might not be defined because it might be uncountable, which is why we restrict to some special sets so that we can define our, so that these sets are countable and we can define the the sum in this set in a easier way. So so for example, like uh, now we will prove that the expected value of a function of a random variable is the sum of that h of x times the probability that the random variable x takes the value small x. So the idea is that if you consider the last thing, this thing, then this will be equal to the summation over x belonging to the image and y belonging to y is equal to h of x of y times the probability that x is x. Right. Now, like we can take uh like in this sum, we can take all those x, small x, we can take all those small x such that h of that small x is y, which is fixed. So, in some sense, we can specialize to h of x being a fixed value y, and the sum that y times the probability that h of x is y. So, like this thing. And now, this will, by definition, be the expected value of the random variable h of x. So, I won't go through the proof entirely, but you can see the proof in these notes. But the idea is just this. So so now with this, like we can prove results like expected value of ax plus b is just the expected value of x times a plus b. Here note that ax plus b is defined as the random variable such that this random variable applied to omega is just a times x applied to omega plus b, and a and b are real numbers. So
Does it matter
can
that they are real?
yes, so right now we are only defining real valued random variables.
Oh, right.
And so, can somebody just tell me why this is true? And we will be using this lemma, this theorem.
This is
So,
because expected value is just an average.
yes, like the idea is right. So, expected value of some random variable, we know that it's just the the average, the weighted average with probabilities of this function. And we also know that sums are linear. So, this sum will break down into x times the sum of expect x times the weighted average plus b times the sum of the probabilities, and this will then be equal to 1. So which will uh, then equal to the a times the expected value x plus b. So like you can try this proof later. It's just like similar to this, and the idea is what Mihir said, that this is just an average and sums preserve linearity. So now we do a similar sort of thing, but now we look for the interaction of two different random variables x and y. So the main benefit of defining a random variable is that we can uh, look for or like consider intersections between like, or like we can consider the relations between two different random variables without having to change the sample space. So that's the main power of defining a random variable. So with that, like suppose that we have two random variables x and y. Now we want to know, if we know that what probability that x is x is, so we know the probability mass function of x and the probability mass function of y. So these two alone do not determine everything. So you cannot tell me what the probability that x is x or and y is y will be, because we don't know how these actually interact. But if we know this probability, so if we know these, so then we will know like everything regarding the values of x and y, which they take like simultaneously. So with this definition, with this we define the joint probability mass function, which is defined as the probability mass function of capital X comma capital Y to be the at the points small x comma small y to be the probability that x is x small x and y is small y. So is this definition clear?
Yes.
Yes. Okay. So the idea is that this event x is equal to x will be some event and y is equal to y will be some other event, and we consider the probability of its intersection. So now this is something that you can check easily, that the sum of the probability mass functions over all x and y is 1. So this is because the joint probability mass function of x and y is just the probability that x and y take some values small x and small y. So if you sum them over small x and small y, then because of the countable union axiom, we will have that this is just the probability of the event capital omega, which is just 1. And you can also check that the sum of the joint probability mass functions of small x and small y over all the values of y is basically gives us the probability mass function of x. So this is an exercise. And now using the because the probability mass function of two random variables is just in a sense the probability that this vector random variable, which we haven't defined, takes the values x and y. But the idea is that if we want to prove that the expected value of a function of two random variables x and y is the summation of this theorem, then the proof will be exactly similar to this one. So this is again like an exercise. So with this, we can actually prove a very central result, which is the linearity of expectation for discrete random variables. So try proving that the expected value of x plus y is the expected value of x plus the expected value of y. And here x plus y is a random variable which takes the value x of omega plus y of omega. So does anybody have a solution? So you can use this theorem, you will obviously use it because so
Can't we just use the other form, the sum over p omega I, p of omega I into x plus y, and then expand?
no, we can use it that only if our sample space capital omega is countable. But this is a general result. Even for uncountable sample space, we just need the image of x and the image of y to be countable. So, like, your proof is correct for capital omega being countable. So, do we get the point?
Yeah. Okay.
Yes. So, actually, linearity of expectation can also be proved by a very similar idea, but uh, that's just uh, that that is sort of just like repeating the proof of this theorem, because this theorem is also proved in that way. So the idea is this, that if image of x is countable and image of y is countable, then we know that uh, the events x is x and y is y will be countable. So for example, if this is image of x and these are the events of image of y. Then then the set of intersections of these are also countable. Now you can specialize to these intersections, and then expected value of the random variable x plus y, you specialize them to these intersections and write them as sum over the probability of this intersection uh, times the value of x plus y at this intersection. And then you write x as similarly you write expected value of x as the sum of the probability of these intersection regions times the value of x at these intersection regions, and similarly for y. And then this result immediately follows from the fact that sums are linear. So do you get this intuitively? Yes. So also notice that on these intersection regions, our random variables x and y are both specified, because these are defined as the regions where x takes the value small x and y takes the value small y. So for now, try proving this using the fact this theorem. So like the proof is just that expected value of x plus y will be the sum of x plus y, small y, times the probability mass functions evaluated small x and small y. Now we can split this sum over these over x and y, such that this is the sum of small x times the probability joint probability mass functions at x or y, and this sum is calculated at all possible values of small x and small y, and plus the similar thing for y.
Actually,
And
the
now,
first term would be independent of y, right? The evaluation.
yes, exactly. So the first term would be independent of y, because this is just the double sum where x belongs to image x and y belongs to image y of the probability of joint probability mass function of x into the joint probability mass function. But this is then just the sum of x times the probability that x is x, because we saw that uh, for joint probability mass functions this is true, this thing. And so we get this is the expected value of x, and the other thing is the expected value of y. So here is the proof if you want to go through. And similarly, we also get that expected value of the random variable a capital X plus b capital Y is a times the expected value of capital X plus b times the expected value of capital Y. So is linearity of expectation is the proof clear after assuming the
Yes.
theorem? Okay. So now we will see some applications. So the linearity of expectation is quite powerful, especially because we don't need x and y to be non-related or independent. It also works for general random variables. So now we will see that in action. So first let's try exercise 6. So suppose we toss a coin n times, and uh, the probability of heads for each coin toss is small p. Then we want to find the expected number of heads. So let's just make this a bit precise, that our random variable x is the number of heads in an n coin toss. So we define an n coin toss to be just a string HTTH, say, where this string has n elements. So now we want to find the expected value of the random variable x, which gives us the number of heads in such an n coin toss. So here our outcomes are the n coin tosses, and our random variable tells you the number of heads. Yes, so now maybe try this for some time. So just as a hint, you want to express the number of heads as a sum of some other random variables. So try to guess a good random variable xi, which when summed from 1 to n gives you the number of heads. So does anybody have any guesses? So consider the indicator random variable over the event ai, where ai is the event that the ith toss is head. So consider the random variable, the indicator function, which takes the value 1 if the ith toss is head and 0 if the ith toss is tail. Now, what is the random variable sum of the indicator random variables ai, where I is 1 to n? It is simply like the sum. So, given an outcome, suppose the outcome is say HTTH, then the first and fourth outcomes are counted as a 1, and the second and third outcomes, like the second and third tosses, are counted as a 0, because this indicator function gives 1 at heads and 0 at tails. So do you see why this indicator function actually measures the number of heads in an outcome?
Yes.
Okay, so here is the interesting part. Now the expected value of number of heads will be the expected value of sum of the indicator function of ai. This is because this is a random variable which measures the number of heads. Now this will be equal to the sum over 1 to n of the expected value of the indicator function iai, and this will be equal to the sum over 1 to n of the probability of the event ai, because we saw earlier that the expected value of an indicator function is the probability of the event. Okay. Now what is the probability of the event ai? It is the probability that the ith toss is a head, and we are given that it is small p. So that means the expected number of heads is simply summation over small p of 1 to n, which is simply np. So is this proof clear?
Yes.
Yes. So initially this might seem ingenious, and indeed it is, but the general thing is that if you want the expected value of suppose number of some objects which correspond to our outcome omega, then this will just be the expected value of our sum of indicator functions of OI, where we define our indicator functions to be 1 if an object OI corresponds to our outcome omega, and 0 otherwise. And then this will be just the sum of the expected value of the indicator functions, which will just be the sum of the probabilities that OI corresponds to omega. Now, also notice that in our uh, tossing the coin example, we did not use that the coin tosses are independent. So even if suppose the first two coin tosses are tangled, so that the our first coin toss uh, gives us a head, if and only if the second coin toss is also gives us a head, even then, as long as the probability of head in each coin toss is small p, we will get that the probability of number of heads is np. So, do you intuitively get this argument here, like this thing, because like this is important. Okay, so let me just explain it again once. So the idea is that so we have an experiment E and we have our outcome omega. Suppose omega corresponds to a number of objects OI, and like omega has the capability of corresponding to a number of objects OI, and all such objects OI, we call these we collect all such objects OI, and we say this to be the set capital O. Then we can calculate the expected value of number of objects OI which correspond to a random omega as the sum of probabilities that a given object OI corresponds to our outcome omega. So now uh, mm, you can try to like prove this just by defining the indicator functions, but the strength in this argument is that we are finding the number of omega which like correspond to a random the number of OI which correspond to a random omega, and we can calculate it just by knowing the probability that a fixed omega correspond a fixed object corresponds to our omega, and this is usually easy to compute. So like let's see another application. So uh, i'll try I'll be doing exercise 8, first part. So suppose we have a random permutation. So what is the number of fixed points in that permutation? And like a fixed point is just the a point which is fixed by a permutation. So which means that a permutation of 1 to n will just be, suppose we have four numbers, then a permutation will be 3, 2, and say 1, 4. Then 2 and 4 are fixed points.
Is the answer 1 to this question?
Yes, exactly. So do you have a proof, like, or an argument?
Yes, the the theorem that we did about above, that was based on double counting.
Yes, exactly. So the probability, so the idea is that the probability that uh, a given position, say 3, the probability that 3 is fixed is 1 by n, because 3 is fixed in n minus 1 factorial permutations and there are total of n factorial permutations. And similarly, for any number I, so the sum of the probabilities that I is fixed will be the sum of 1 by n over 1 to n, which will just be 1. And because of this uh, above argument, this one, we know that this sum, the sum of the probabilities that I is fixed, is the sum of the like the indicator functions over the events ai, where ai corresponds to the event that I is fixed, and then this will just be the expected value of the number of fixed points. This is because this will be the expected value of the number of I which are fixed, which is precisely like the number of fixed points. So like do you get the idea of the linearity of expectation? So this way of using it.
Actually, in this problem using double counting, you can also get an interesting identity.
Yes. Uh, but like we just need to calculate the number of fixed points. So do you mean like okay? I get what you mean. So are you calculating it in this way? Like the probability that the number of fixed points is some a times a.
Right, right. So that is
Yes,
NCA into dearrangement of n minus a.
yes, exactly. But that is not easy to compute. That's why we rely on linearity of expectation,
Okay.
because and but that's right. Like you can get uh, lots of identities just by using the just by computing the expectation of a random variable x, then equating it to our definition. So like we don't have a lot of time left, I think. So like I won't do the exercises now, but like the coupon collector problem is really nice, so I do encourage you to try it. And you will be using exercise 7 to solve the coupon collector problem. So uh, like maybe I'll just do one of the Olympiad problems which uses linearity of expectation. So let's just try 1999 C4. So this uses another concept also, which is that suppose we have a random variable x, and that expected value of x, we know it is some c. Then for some outcome omega, x will take a value that is more than c, and x will also take a value that is less than c. So this is basically just equivalent to a sort of pigeonhole idea, or like you can say that just by writing expected value of x as a definition as we gave, and then like by a simple inequality argument you can get this. So but do you see why this is true? This should be true.
Yes.
Yes. Okay. So now like let's try this problem. So uh, the problem is that suppose that A is a set of n residues modulo n square. So wait, so I think this problem might be a bit technical, but okay, let's just do it. So let A be a set of n residues modulo n square. So like Does everybody know like a little bit of modular arithmetic?
Yes.
Okay, so A is a set of n residues modulo n square. Now we need to prove the existence of a set B of n residues, so that let's say of at most n residues, so that A plus B is the set A plus B, which is defined as the set of A plus B such that A belongs to A and B belongs to B, has at least n square by 2 residues. So is the statement clear?
Yes, it is.
Yes. So now we also let, just for convenience, we also let allow B to have repeated elements, so that like we can make B to have exactly n elements, including repetition. So do you get what I mean by this?
Yes.
Okay. So now we will, to prove that there exists such a B. So what if we proved that the expected number of elements in B, where we choose everything uniformly, is greater equal n square by 2? Then we will have shown that there exists such a B, such that
Expected value of A plus B, right?
yes, expected value of the yes, you're correct. So expected value of the cardinality of A plus B, where we choose B uniformly. So in general, we can take B to have any distribution, but usually we only care about uniform distribution because it's easy to compute. So so is this idea clear, that if we choose B uniformly, then if we calculate the expected number of elements in A plus B and it turns out to be greater equal n square by 2, then we will be done.
Yes.
Okay, so now like I'll give you about 1 minute to calculate this expectation where
Just to
B is
confirm,
uniform.
B, the number of choices for B would be n square raised to n, right?
Number of choices for B. So
Because we are allowing repetition, so it must be n square raised to n, right?
let me just check once. So the first element can be chosen in n, the second can be in n, and we can choose, and yes, and exactly. So it will be n square to the n. So this is
Okay.
because the first element can be chosen in n square ways, and similarly all the other elements, and we are allowing repetitions. So like try this for maybe like 1 minute, because like we don't have much time. So let me just, do you see how we will be applying our indicator function idea in this? So we need to calculate an expectation which is of this form: the expected value of number of elements I belonging to 1 2 till n square, such that I also belongs to A plus B. We need to calculate this. Is this clear? Because this will just be the cardinality of A plus B. And now this is the expected value of number of I, such that there is some property about I. So by our indicator function idea, this will be the summation over I is from 1 to n square of the probability that the particular I actually belongs to A plus B, where B is chosen at random. Is this clear? Yes, so like this can be like you can prove this just by considering indicator functions and then like by the same process as we derived for like the n coin tosses thing. And like the idea is that is this one, that if you have like any set of objects corresponding to an outcome, then you can calculate the expectation of a number of objects as the summation of the probability that a particular given fixed object corresponds to our omega, and omega is chosen randomly. So now how will you calculate this? So this is the summation over 1 to n square of the probability that our I belongs to A plus B. Here notice that A is fixed and B is random, uniformly at so B is, so each element of B is chosen uniformly at random. So B is B1, B2 till Bn, where all these are chosen uniformly at random from the set 1, 2, 3 n square. Now, what is the probability that I does not belong to this set? So that will be equal to the probability that I is not equal to B1 multiplied by the probability that I is not equal to B2, and so on. Now the probability that I is not equal to B1, what is this value? Yes, so I think like Mihir, like did you get this part, like or were you like you?
Hello, I was disconnected for 2 minutes. What were you saying?
Oh, okay, no problem. Uh did you get that the expected number of I belonging, so we wanted to calculate the expected value of the cardinality of A plus B, right?
Yes.
And we have proved that if we show that the expected value of the cardinality of A plus B is greater equal n square by 2, then we will be done.
Yes. I attended that part. Then yeah,
Okay.
from this part I did not.
Okay. So the idea is that the expected value of number of I belonging to 1 to n square such that I also belongs to uh, the set A plus B, this is what we have to calculate. And this will be the summation of the probability that a given fixed I belongs to our set A plus B, where
Yes.
B is chosen randomly. So now this will be the summation of 1 to n square of probability that I belongs to A plus B. Here, like this was just to emphasize that B is random. So now B is the set construct. It is constructed in a way like we choose B1, B2, and Bn, which belong to B, and all are chosen uniformly at random from 1 to n square, right? Okay. So now the probability
Uh,
that
Set A has distinct elements, right?
yes, set A has distinct elements.
So
So
for each element of set A, there is an unique element, so such that the sum of them is I, modulo n
yes,
square.
yes, exactly. So the idea is that we will calculate the probability that I does not belong to A plus B, and then take 1 minus. So the probability that I does not belong to A plus B will be the probability that I is not equal to B1 multiplied by the probability that I is not equal to b2, and so on till the probability that I is not equal to bn. Is this thing clear?
We can also evaluate probability of I equal to B1 also, right?
Yes, but then I can be both b1 and b2 at a time, so we can't use the product rule because you get why, right?
Okay, yes, right.
So now we will calculate what is the what is the probability that I is not b1, and notice that b1 is a random number in 1 to n square. I is okay, like by this I mean that I does not belong to a plus b1. It's a bit of a mistake. So we want to calculate the probability that I does not belong to a plus b1 multiplied by the probability that I does not belong to a plus b2, and so on. So do you get why we calculate this?
Yes.
Now what will this be?
Is it belong or does not belong?
Does not belong. So
That would be n square minus n.
uh, no, so fix an I. Now what are the possible values of b1 such that I belongs to a plus b1? There will be n such values.
Tejas,
N factor.
try to wrap up as soon as possible.
Yes, I just need about 1 minute or 2 minutes. So
Sure. Yeah.
okay. So what are the possible? How many values of b1 are there such that I does belong to a plus b1? So that is n
N.
square minus n. Wait, n, right? Yes,
Yes.
exactly n. So what is the so there are exactly n square minus n values such that I does not belong to a plus b1. That means that the probability that I does not belong to a plus b1 is n square minus n divided by n square. Do you get why this is the case?
Yes.
Yes. Now, this is just 1 minus 1 by n, and it will be the same for each of these numbers, like each of b2, b3, because all have uniform distribution. So we get that the probability which we want to calculate, which is uh, the probability that I does not belong to a plus b, is 1 minus 1 by n whole to the power n, because this is the product of probabilities that I does not belong to a plus bi for I is 1 to n. So now we just have to prove that 1 minus 1 by n to the n, which is the probability that I does belong to a plus b, because of the complement thing. We need to prove that this is greater equal n square. This is greater equal half, because then we can calculate like the cardinality of such a set to be n square by 2, right? So we just need to
Yes.
prove that 1 minus 1 by n to the power n is less equal half, but uh, this is a fact, because 1 minus 1 by n to the n is a decreasing function. Yes, it's a decreasing function. That means that this is true, and its limit
And
is
limit is
1.
1 by.
Yes, exactly. So the limit is 1 by e, which is less equal 1 by 2. So that means like we have solved this. So do you get like the brief idea of the proof? Like you can just assume this for now if you like don't know that decreasing part. So like now like I will tell you like which exercises to try and so on. So like I said, like exercise 7, uh, in exercise 7 like you can just calculate this by expected value of x by just the definition and finding the probability mass function. And this is mainly so that you can use it to like try exercise 10. So do try exercise 10. And also like this problem is also very nice, but it is still quite hard. And this is for uh, calculating expectations. And uh, these two problems are existence proofs, in which you will generally in an existence proof you will find a distribution. That means you will vary something randomly and then calculate the expected value of our random variable x and prove that it is greater than the constant c, which we have to prove that x takes. Right, so and that's it for now. So uh, does anybody have any doubts? What?
No, I don't have any doubt.
Okay. Okay then.